the major responsibilities of the United States Geological Survey is the preparation and maintenance of a series of topographic maps which will cover the entire United States. One of the most useful maps produced is the standard quadrangle map, bounded by 7½ minutes of longitude and latitude at a scale of 1 to 24,000, or 1 inch equals 2,000 feet. Topographic maps record the physical characteristics of the terrain as determined by precise engineering surveys and measurements. The brown contour lines, the distinguishing characteristic of topographic maps, show the shape and elevation of the land surface. Valleys are shown by the contour symbolization. Rivers and streams are shown in blue. The works of man and the names given them are shown in black. Man-made objects are shown with representative symbolization. The early map makers sketched the terrain in the field, using instruments that made measurements on the ground, from which distances and heights could be determined. With the development of photography in the mid-1800s, cameras were designed to take terrain photographs, from which accurate measurements could be made. Soon, cameras began to be lifted into the air. Instruments capable of making measurements from aerial photographs were designed, and photogrammetry developed rapidly. Photogrammetry means obtaining reliable information about physical objects and their environment by measuring and interpreting photographs. Today, photographs are taken with high-precision aerial cameras, and most maps are compiled by stereophotogrammetric methods. After an area has been authorized for mapping, the planning and procurement of photography are the first steps in the mapping process. The necessary calculations are made on a flight design worksheet. The flight planner chooses the best available base map on which to delineate the design flight lines. The final plan gives the location, length, and spacing of flight strips, the distances between exposures and between flight lines expressed as ratios, the focal length of the camera, and the heights above sea level for the various flights. The photographs are procured from qualified private contractors who use precisely calibrated aerial cameras that meet rigid specifications. The flight plan must be followed with care, and specified altitudes must be maintained. The photographs must be taken when there are no clouds, no snow, no excessive shadows, and minimum foliage. The proper aperture must be set. The forward overlap between successive photographs must be carefully monitored to ensure adequate stereo coverage. Upon completion of the photography, the film is developed and inspection prints prepared and checked for compliance with specifications. Forward overlap, side overlap, and image quality are checked. Upon acceptance, horizontal and vertical control planning begins. The centers of the new photographs are plotted by correlating the imagery on the photograph with the base map detail. The distance between photo centers represents the overlapping portions of two successive photographs. The topographic map will be compiled from the three-dimensional optical model formed in a stereo plotting instrument from the overlapping areas of the photographs. Each stereo model must have corner control points to establish accurate scale and elevation, and to reference the stereo model to the map projection, which represents a portion of the surface of the Earth. The rays show the relationship between the control points on the ground, their images on the photograph, and the camera. The basic framework of existing control on the project is delineated. The plotted centers of the new photographs define the flight lines. The location and density of the additional control points, which must be surveyed in the field, are indicated by the control planner. This framework will be expanded by photogrammetric methods to develop the model control points shown by the small green symbol. The field control points selected must be field identified for use by the photogrammetrist. The best identification method, called pre-paneling, is to set panels around an existing control mark before the mapping photographs are taken, using a material which gives maximum contrast between the panel and the ground. The control point is identified by the panel image on the photograph. This gives the photogrammetrist a positive identification and a precise location of the control mark. The planner symbolizes this as he plots and labels the existing horizontal and vertical control points on both the photographs and the control plan. The plan showing the additional ground control points is sent to the field. Field crews establish elevations and positions for these additional control points. The use of helicopters for the transportation of men and equipment has greatly reduced the time required to carry out field survey operations. The electronic distance measuring devices achieve a high order of accuracy for the measured distances in the field control network. The photogrammetric operations which follow depend on the accuracy of this basic framework of field control points. In addition to establishing the control points, the field party identifies and classifies the features to be shown on the map. Names for geographic and cultural features are obtained. Control points which are not pre-paneled also must be identified. One method is post-paneling. The control marks are paneled at the time the additional points are surveyed. An airplane is hired locally, and these panels are photographed on 35mm film from a flight height selected to give an adequate scale and coverage of the area around the panel. The use of natural panels is a common solution to the problem of control identification. Natural panels, such as road intersections and small bushes which are imaged on the photographs, are identified and located by precise field surveys. Upon completion of fieldwork, diapositives, which are positive photographic prints on glass or film, are prepared. Diapositives are made under darkroom conditions, usually in a projection printer, which is basically a high-precision ratio camera. This printer, filmed under lights, uses an automatic electronic velocity modulation type of photographic contrast control to produce a full-size diapositive. The printer has several functions: compensation for the distortion in the system of lenses in the aerial camera, the printer, and the projector; correction for earth curvature, which is a factor at higher flight heights; and a transfer of the primary calibration data from the aerial camera negative to the diapositive. The diapositive is developed in film tanks with agitation by the gas burst technique. The development conditions are controlled to produce a diapositive, having a density range which permits the formation of a usable stereo model and accurate plotting. Aerotriangulation begins with marking the identified control points on the diapositive by drilling the emulsion. For projects that were not pre-paneled, the panel positions representing the control points imaged on the 35mm film are transferred to corresponding positions on the diapositive. The framework of field control points is expanded by a photogrammetric process called aerotriangulation. Aerotriangulation develops the required model control points shown by the green symbol. The planning phase of aerotriangulation involves the selection of tie points which are common to adjacent strips, and model pass points which are common to adjacent photographs in each flight strip. The plan points form the framework to fit the models together. The drilled diapositives are placed in high-precision stereo plotters. A relative orientation procedure creates an optical terrain model, seen in 3 dimensions by the operator. He uses the hand wheels and foot pedal to position the measuring mark on what he sees as the ground at the drilled points. The model coordinates of the drill points are displayed on a console and are punched on a data card. The cards are formed into decks and processed by computer programs, which develop, adjust, and transform the model coordinates into the coordinate system of the ground control. The output of the adjustment program is a punched card deck of ground coordinates and elevations for all the points to be plotted on the map manuscript. This deck is processed by another program, producing a magnetic tape, which provides the input commands for an automatic plotting system called the autoplot. The autoplot automatically prepares the map compilation base by scribing a line to define the geographic reticule, plotting the state plane coordinate system grid ticks, the basic control points, the photogrammetric control points, along with elevations and identification labels. The data plotted on the map base in conjunction with the data on the photographs provide the compiler with the information necessary to orient the stereo models in the compilation phase which follows. A double projection type stereo plotter called the ER55 or ballplex is used chiefly to compile steep terrain. The reduced size diapositives are properly positioned in the holders, placed in the projectors, and the projector motions used to orient the model. This orientation procedure results in a recovery of the relationship established by the aerial camera at the successive exposure station with respect to the position and attitude of the camera at the preceding exposure station. Terrain with small relief differences is photographed from lower altitudes, and accurate measurements are made from full-size diapositives in optical, mechanical, or double projection type stereo plotting instruments. Some of the optical mechanical plotters used are the Wild A7, which is basically an aerotriangulation instrument. The Wild B8, which has a drawing device in the tracing stand that permits the map to be compiled at model scale or through the pantograph. And the Kern PG2, which also uses full-size diapositives. On this plotter, the diapositives remain in a horizontal position during the entire orientation and compilation procedures. The system of horizontal rails supports the projectors as the tracing stand to which the projector carriages are connected is moved in the X and then the Y directions in the model. These optical mechanical instruments use a train of prisms, lenses, and mechanical motions to form the model, which is viewed in 3 dimensions after an orientation procedure. The Kelch plotter, which also uses full-size diapositives, is a double projection type instrument. The model is formed by conjugate image rays projected from each diapositive onto the viewing platen. A viewing system called a stereo image alternator flashes images alternately from each projector. A rotating shutter in each projector generates these flashes. The images are seen on a platen through a synchronized viewing shutter and are so phased that the left image is presented to the left eye and the right to the right eye. The mind coordinates these images to give the operator the impression of a 3-dimensional optical model. A relative orientation procedure arranges the projected images to form the stereo model. The rotational and translational motions of the projectors are used to establish the position and attitude of the pair of projectors with respect to each other. As with the ER55, the relative position and attitude of the camera at successive exposure stations is recovered by the projectors. An absolute orientation procedure relates the model to the surface of the Earth, as represented by the map base, by means of correlating the drill control points as seen in the model with their respective positions and elevations plotted on the map compilation base. The correlation is transferred from the model space to the map base through a precisely calibrated reduction pantograph. The relationship between model and map compilation base is maintained by metal registration studs taped on the granite plotting surface. The platen, containing the illuminated measuring mark, is connected to a digital counter through a series of gears, which are changed for different model scales. Accurate elevations are read by positioning the measuring mark on the ground surface in the optical model of the terrain. The compilation map manuscripts consist of the map compilation base, the woodland base, and the contour base. These components are registered to each other by holes punched at each corner. Metal studs inserted in these holes permit a precise recovery of the initial registration for any combination of bases. The map-worthy planimetric detail is compiled on the map compilation base by keeping the measuring mark in contact with the apparent ground and tracing out the features. Then the map compilation base is removed from the granite plotting surface and the pencil planimetry is carefully scribed over a light table with proper symbolization. Special tools called gravers are used to cut out the lines drawn on or transferred to an opaque coating on a sheet of clear plastic. A transparent image is produced, and the scribed negative may be utilized in the same manner as a photonegative in subsequent photographic processes. If the terrain contains ground cover, which is to be mapped as one of the classifications of woodland, the woodland base is placed on the registration studs. The areas of vegetation outlined from the model and subsequently scribed. The contour base is registered. The elevation difference of the ground in the model determines the series of contours which will be traced that portray the terrain. The measuring mark is set at a contour elevation, and as the operator traverses the model surface at that height, the contour is scribed directly. This is repeated for the range of contours in the model and completes the photogrammetric compilation of the model. The information scribed on the map compilation base, as well as the contours which were direct scribed, are transferred to the contour base by a photographic process. The direct scribed contours must be rescribed. This base provides the final contour reproduction manuscript when cartographic standards are met. Otherwise, the contour base is rescribed during the color separation phase. A composite print is made from the map compilation base and the contour base and reviewed. The compilation is checked not only to assure that the detail annotated on photographs has been completely and correctly compiled, but also to check whether or not the contours appropriately depict the shape and elevation of the land surface. The materials are then sent to the Field Surveys branch for completion of section line detail and further checking. Then to the branch of cartography for color separation and editing. The color separation manuscripts are sent from the regional facilities to Washington, D.C. for printing and publication. The standard 1 to 24,000 scale topographic maps prepared by the United States Geological Survey have many uses as fundamental tools for planning and executing projects that are necessary to our modern way of life. Intelligent and efficient development of our natural resources depends on the availability of adequate topographic maps. Thoughtful and intelligent utilization of these resources will make it possible to maintain the delicate balance of life on our planet.